Okay, today we're going to be looking at a couple more examples for solving both logarithmic equations with e and exponential equations with e. Okay, so let's look at this first example. We have e to the x plus 1 power minus 9 is equal to 3. First step is always to isolate the base, because you can't change the form without the base being isolated. So you do need to identify the base. In this example, the base is e, which has an exponent of x plus 1. Once you identify that, you can see that there's something over here with it that does not need to be there, which is the 9. So we need to move it to the other side. So we get e to the x plus 1 equals 12. Of course, this is a exponential equation. So to solve it, we would change its form into a logarithmic equation. Now the log is going to have the same base as the exponent, which is e. So the way that we write a log with base e is ln, the natural log. And then these two can switch their place. So on the inside of the natural log is 12, and on the other side we have x plus 1. Keep in mind we are solving for x, so we do need to get rid of anything that's over there with the x. In this case, we have a 1 plus 1, so we do need to get rid of that. Now, very important, do not subtract that 1 from 12, okay? The 12 is inside the logarithm. It can't be touched by this 1, okay? It's not going to work. Once we have what x is by itself, we can use our calculator to calculate an approximate value. Okay, so we're going to put natural log of 12 in the calculator, and then we will subtract 1. Okay, so natural log of 12 is this, subtract 1 is this, and we'll round it to 4 decimal places, so 1.4849. And that is the approximate value of our solution for number 1. Now, that problem started in exponent form. The next problem starts in log form. Okay, natural log of x plus 1 is equal to 3. Doesn't matter what form it starts in, these steps are essentially the same. First thing we want to do is make sure the base is isolated, which it is already. There's nothing over here with the logarithm. Okay, there's no multiplication, there's no addition or subtraction, there's nothing over here. So we can just go ahead and skip the changing form. Okay, now we are in log form, which means we're changing to exponent form. The base of the exponent should be the base of the log. The base of the log here, since it's a natural log, is e. So the base of the exponent will also be e. And then these two can swap places. So the exponent will be 3 and x plus 1 will be on the other side. We are trying to get x by itself. That's the goal here. So since it's 1 is being added to it, we will have to subtract 1 from it. So we get e to the third minus 1 is equal to x. And this we can calculate. Okay, our calculator will do this and give us the value of x. So we're going to do e to the third power, and then we'll subtract 1 from whatever that is. E exponent 3, subtract 1 from that, so 19.0855. All right, and that is the approximate value of the solution for number 2. All right, number 3, we have the natural log of 3x is equal to 8. Of course, we would start this problem by making sure that the base is by itself, which in this case, the log is by itself. But of course it is. There's nothing multiplied, nothing added. So we can jump to the next step, which is to change the form here. Okay, so changing the form would put us into exponent form, which would mean our base is e, since the base of our logarithm is e, and then these two can switch. So the 8 will be the exponent here, and then 3x on the other side. Then we can solve for x, of course, because x is not by itself, and we need x to be by itself. It's currently being multiplied by 3. We can get rid of multiplication by 3 by dividing by 3. We get e to the 8th power over 3 is equal to x. And once our variable x is by itself, we now have something that we can put into the calculator to give us an estimate of the value. So we'll do e to the 8th and divide that by 3. So e exponent 8 is this number, and then divide that by 3 is this number, which will round to 4 decimal places, so 993.6527. 993.6527. And that is the estimate for our solution for number 3. Now, one more type of problem I want to look at is a real life problem. When would you use this Euler's number? Okay, what's important about this E number? Okay, we said it's like pi and that it's important like pi, but like when would you ever use it? One of the most common times you would see it is with interest. Okay, interest on like a bank account or a loan or something like that. Commonly, continuously compounded interest. Okay, this would be interest that doesn't accrue monthly or doesn't accrue yearly, but it accrues nonstop. Okay, interest that's always occurring, like every second of every day interest. Sounds worse than it is. It's really not that bad. But the equation that you use for continuously compounded interest is right here. Y equals P times E to the R times T power. And everything in this formula represents something. The Y is, of course, the final amount. That's what you would be calculating. The P is the initial or principal amount. We'll just call it initial amount, but you may see it written as the principal amount. E is Euler's number. That's just a number. It's in the calculator. R is the rate, and that rate should be expressed as a decimal. It will be given as a percentage. You need to divide it by 100 to express it as a decimal. And T is the number of years, the time, which is measured in years, so the number of years. All of this information can be found from the problem. So let's start. When Angelina was born, her grandparents put $3,000. Okay, so this is starting amount there. We have 3,000 as her starting amount or her initial amount. Put $3,000 in a fund paying 4%. Okay, so it's paying 4%. So the rate is 4%. Divide that by 100 to get a decimal, 0.04. Compounding continuously. Okay, this is how you know that you're using this formula. Okay, this is the compounding continuously formula. So if the problem says that it's compounded continuously, you would use this formula. Assuming there are no withdrawals or deposits, and she goes to college at 18. Okay, so 18 years is how long it's taking them, how long that money is going to be there. What is the expected balance? So that's what we do not know. We do not know the final amount. we can use this formula to calculate the final amount. So we have y is equal to P, the initial amount, which is 3,000, times E to the R times T, so R is 0.04 times T, so times 18. Okay, so all we have to do is calculate the value of this. So this is all stuff we can plug into the calculator. So the way that you want to do this to plug it into the calculator is you first want to plug this in, e to the 0.04 times 18. And whatever you get there, then you multiply that by 3,000. So let's calculate that. Now notice I put parentheses around the exponent, and that's because I need to tell the calculator to do the exponent first, and then raise e to whatever that exponent is. So e exponent parentheses 0.04 times 18, close the parentheses, and that's equal to this, 2 point, etc. That is the value of this yellow box here. Okay, so now whatever that is, I'm going to multiply it by 3,000. So times 3,000 is equal to, and this is how much she will have when she turns 18. She'll have $6,163.29 of 30 cents. Not bad. I mean, if she kept it in a bank account that wasn't compounding interest, she would still have $3,000. Okay, so compounding interest can be a good thing. All right, and that's it for this lesson.